Welcome back. So now we're going to look at naming ionic compounds. So we're going to put everything together. And I think that's what gets me really excited about chemistry, is that the individual concepts aren't that bad, but when you put them together and you kind of string one on top of the other, it gets pretty exciting pretty quickly. So what's the compound? So maybe I could go ahead and do sort of a two-parter. Name and write the formula of the compound formed between, oh gosh, what would be a good one? Sodium and phosphorus. So the very first thing to recognize is that sodium is a metal and phosphorus is a non-metal. So you instantly know it's going to be an ionic compound when you see this pairing. So it's definitely going to be ionic because you've got a metal, all right, M for short, and you got a non-metal, all right, N for short. So how do I know that? Well, if I look at my periodic table, which I'll very quickly kind of sketch out here, sodium is like all the way over here, and phosphorus is very poorly drawn, but all the way over here. And so we can see you've got the metal side and you got the non-metal side. So definitely going to be ionic. How do we know what charge these things have? Well, first of all, we got to know what symbol sodium is. Sodium is Na. It is in group 1A, so it's going to have a charge of 1 positive. Phosphorus is P, and it's 3 away from the noble gases, so its charge is going to be 3 minus. And you might want to just pause the periodic table here, pause the video and look at your periodic table and make sure you're happy with those charges. Okay, so we got to do two things. We got to write the name, we got to write the formula. So I think probably the easiest thing to do is to go ahead and write the name, and Na plus is just sodium. Does sodium have more than one charge? Well, if it did, we would write the charge in Roman numerals afterwards, but we wouldn't have known the charge anyway if it had more than one, unless it is in the center of the periodic table or it is low down here. So unless it's a transition metal or a heavy metal, it's only going to have one charge here. So sodium is always sodium, 1 positive. So sodium ion, or just sodium for short. And we're going to go ahead and write phosphorus next. So phosphorus, and remember, how do we name this thing, right? So the ion, we just remove the ending, and the ending here is going to be ORUS, and we switch it out for IDE. So when we name an ionic compound, we just name those two parts together. So this thing together would be sodium phosphide. So when we name them, we just name the cation first, and we name the anion second, and we just sandwich them together. So I didn't explicitly call out, right? We have to name them these ways, but by doing the example, hopefully that illustrates how we do it. Now, what about the formula? So the formula we can get by crisscrossing. We can take the 1 positive and make it a 1 over here, and the 3 negative and make it a 3 over here. And so it would be Na3. Remember, we ignore the minus. And then it would be P1. And remember, when we write formulas, if there's 1 of something, the convention is not to write it at all. So it would just be Na3P, and that would be sodium phosphide. So let's do one more, and then I'll give you one to try. So let's bring up a new slide. Okay, so how about this one here? So what do you get in terms of the name and formula when you react magnesium with, oh gosh, what would be a good one? How about sulfur? So first of all, we've got a metal, magnesium, and we got a non-metal, sulfur. So we know that because if we look at our periodic table, which I'll quickly sketch out, then we've got magnesium right over here, and we got sulfur somewhere about here. So they're on opposing sides of the periodic table. We got metal, we got non-metal. So it's definitely ionic. So later on, we'll look at covalent, and we have to name those differently. So we'll need to always make sure we know which is which. What do we want to do first, name or formula? So let's write the formula of the ions first. So magnesium, based on where it is in the periodic table, it's in group 2A, so it would have a charge of 2 positive, so make sure you can locate it on the periodic table. And sulfur is in group 6A, it's 2 away from the noble gases, so its charge would be 2 minus. Let me pull up a more detailed periodic table and look at that once more. All right, here's a better periodic table. So here's magnesium, and here is sulfur. And so we can see that these are in group 2A, so 2 positive, right? So I always count from the left, so 1 positive, 2 positive, and then sulfur is 2 minus, so I always figure it out by counting from the right, and I know the noble gases are 0, so 1 minus, 2 minus, so sulfur is 2 minus, and magnesium is 2 positive. So what do we want? We want the formula. So this is one where the crisscross method actually gets us in trouble, because the 2 there and the 2 there, you might think it's Mg2S2, but you always simplify. So 2 to 2 simplifies to 1 to 1. So instead of writing Mg2S2, you write Mgs. And we name it by just naming the 2 ions. So Mg2 plus, that is just magnesium, because it doesn't have a variable charge. We don't have to say magnesium 2. And sulfur, the UR switches to IDE. So magnesium sulfide would be the name of that compound. Mgs would be the formula. And remember, do we write the charges in? No, we don't. So in the formulas, the charges have canceled out, so they're never written in. So we are done. Well done. So in the last example, we looked at magnesium sulfide, and I said that the magnesium ion and the sulfide ion, they have equal and opposite charges, so they just come together 1 to 1. And if you've ever looked, actually, unless you have an electron microscope, you've probably never looked, but the ions themselves, there's not just one of each in the compound. They actually come as a repeating pattern that looks something like this. So you've got 1 magnesium for every sulfide, but they don't just stop after you've got 1 of each like a molecule would. They actually are just this repeating pattern. So in actual fact, we can kind of imagine these as sort of beads on a lattice. In fact, we call this a crystal lattice. So these ions actually arrange positive, negative, positive, negative, positive, negative, like so, and they arrange in such a way you've got an equal number of one charge to the other. So that would be magnesium sulfide if you were to look at it close up. These ions are very well attracted to each other, so opposites attract. So they actually tend to have very high melting points and boiling points. It takes a lot of energy to break these apart. So regular table salt, you've got to melt it. Actually, you can't really melt in a regular oven. You need to take it up to a couple thousand degrees Fahrenheit before it melts. They also are very crystalline. If you've ever seen little salt crystals, they look like beautiful little tiny cubes that kind of glint and catch the sunlight. And so this regular array causes that the crystals have a very beautiful geometric shape. So gorgeous, beautiful stuff, huh?